We are very happy to have Sara Faridi from Dalhousie University, and she will tell us about the Algebra and Combinatorics of Extremal ideals. Is that correct?
Well, I don't know because I forgot my title.
Ah, okay.
Yeah, but I was going to talk about extremal ideals. So thank you so much for inviting me. The organizers, this is a beautiful conference in what I consider one of the most beautiful cities in the world. Thank you, Karen. Pretty much everything to you. I don't know how to start crying. But after a whole day of singularities and so on, I kind of feel bad. I'm going to talk only about combinatorics and monomial ideals, and there's some algebra there, but we will never leave the polynomial ring, and we won't really care about characteristics, but I think low characteristics usually gives you trouble anyway, so that's Kevin mentioned earlier. Okay, so this is joint work with the people here, so I'm just going to go through the names of the people. Trung Chau is a former student of Anurag Singh, and he's now in India, a postdoc. Susan Cooper, I think people know Susan Cooper, Sabine El-Khoury, Sara Mayes-Tang, an academic sister, Susan Morey, Liana Sega, and Sandra Spiroff. They are part of the original Women in Commutative Algebra WICA group that we had about 2019. It was a conference organized by Karen and by Irena, and also Emily Witt and Sandy Spiroff are not here. So this was our group, and a big thank you for that. I actually sort of survived, and even I'm ashamed to say enjoyed the pandemic, because I got to do a lot of great math with these people while we were all shut down in all of
Yeah, and I had that experience too. There's nothing else to do.
Yes.
Nobody not gonna want to do work.
Yeah. But you can't say that in this company. So.
Yeah, my kids were grown up enough, so it's different.
Yeah. Anyway, and then like about 4 papers or 5 papers later, we recruited people. We went to another bank meeting. Art Duval from Texas. He is a combinatorist, and Hasan Mahmood is my student, and his contribution is that whatever I'm saying today, I will probably not have time to mention it, but later, whatever I'm saying today is only working for square-free monomial ideals. For other monomial ideals that are not square-free, these things don't work the way you expect. You have to have more machinery. Okay, and who else is here? Thiago Holleben is my student, so Trung and Thiago and Art joined 3 of us, and we did a lot of combinatorial things. So most of the algebraic stuff that I talk about today, if I make it to the end of my talk, so I think I will start from the end of my talk actually, is going to be due to this latest group. So I put all so that's a permutation sigma of these, where sigma is in S6. The biggest group is 7 co-authors. And 6 co-authors. Okay, and I'm going to put here what the message is of the whole talk, and that is, the message is, if I is in ideal in a polynomial ring, so let's call it R. Should I write bigger or generated? Yes, no, good. Bigger? Okay. Generated, yes, by 2 square-free monomials. So let's always think of I like this. And P is a property. Typically an algebraic property. So it's still kind of open what the property is, but I'm going to list a bunch of them that we know about. And R is an integer. Then to check P for I to the R, it is enough to check it for EQR. And this EQR, so EQ is the Q extremal ideal. which I will try to remember to define here. But right now the definition doesn't matter. And the message is here. This is what I want you to take home. So there is this one ideal, it's combinatorially defined. So for example, if you want to check an ideal is integrally closed, it's enough to check it for that. If you want to check if an ideal is, if you want to find symbolic powers, you find symbolic powers of these ideals. If you want to check an ideal is normal, you do this. Symbolic defect, you do this. Bounds of Betty numbers come from this. So powers of monomial ideals, square free monomial ideals, their properties are determined by extremal ideals. So this is the conclusion of the whole talk. And I will try to now tell you the story of the extremal ideals, how they're constructed, and I'll try to get as far as I can with the properties. And again, this list of properties is ever growing, and a lot of this is work in progress. This is only the second time I'm giving a talk on this. And the first time I didn't really make it to the end. So I'm always, because it's a sprawling thing, and I get digressed, so this is what I want you to take home, okay?
In case anyone's confused, you said square free, but you wrote square.
Oh, thank you. That is important.
Yeah.
Square free. Okay, so the question we started from or a question we ended with, where we actually were working on something else, was, so I'm not going to write this again. I is always generated by Q square free monomials, and R is always a positive integer. So how big can the minimal free resolution resolution, I will call MFR, of I to the R B. So what are the bounds on this resolution? And for any monomial ideal, the bound on the resolutions are binomial coefficients where the top part is the number of generators, the minimal generating set or the non-minimal generating set, but then it's too big. We already know that.
Are you measuring largeness or?
So largeness means how large can it be? So
Lengths or ranks of the modules or
ranks of them.
ranks of the modules?
So maybe I should write this down, right? So a minimal free resolution, this is not a combinatoric, so I already graded free resolution. So a minimal graded free resolution of I, of any monomial ideal, well, actually any graded ideal in this case, of R, so let's call it ideal J, is going to be of this form, like R to the beta 0 J, and then J is an N, then O plus R to the beta 1 J, and then you twist by J, etc., etc. And for monomial ideals, you can actually count these J's by using monomials that appear as the LCMs of your generators. So you can subindex this. So we can define this a multigraded resolution. So that becomes something like Rm to the beta 0m and you sum over monomials in the LCM lattice of J. And this means that coset of LCMs of generators of J. Okay? So this is beta 0, and then beta 1. And then so on. Okay? And then the beta ij will be the sum. Your graded Betty number is going to be the sum of beta ims, where m is in the LCM lattice, and degree of m is equal to j. Okay? So a lot of this follows from what's known as Hofstra's formula. And also the topology of the LCM lattice can give you this resolution. So this multigraded resolution is a topological resolution. So you can get it by basically the Stanley-Reisner ring, Alexander dual. You can do it by the LCM lattice. You can use discrete Morse theory. You can use whatever you want, Taylor resolution. And there are these homotopy equivalences between these topological objects, which always end up giving you the same thing. So the general idea here is how can I enumerate these topologically? So Taylor's resolution says that you can always, let me say the upshot of Taylor's resolution. So beta I is always less than or equal to Q choose I, where Q is your number of generators. Okay. And why is that? Is because Q choose I is the number of I faces of a simplex. So if I have 3 generators, then a 3 simplex is a triangle. So here my J is M1, any monomial like M2, M3. So what you do is you homogenize this. So every face of it is going to have the LCM of its vertices. And in here you have LCM of 1, 2, 3. Okay. And then there are boundary maps. For example, for this simplex, there is this familiar, hopefully, boundary map of the simplex of delta going from, let's say, from I to I minus 1. This is the vector space in this case generated by all the I faces. This is the vector space generated by all the I minus 1 faces. We can consider them as chain groups, but we could do. And this is the boundary, which takes, for example, an edge to the sum of its vertices. So this is going to give us a resolution because when I'm taking an edge now, it's like I homogenize the edge. I say M1, M2, and in the middle I write LCM of M1 to M2, M1 comma M2. And this map will be my differential for the resolution, but it will be a homogenized map whose entries are of the form LCM of M1, M2 divided by like M1. LCM of M1. Here I did just 1. So the LCM of a face to the LCM of its subface, and the other entry will be a matrix of this form. So this is called the Taylor resolution, and since each one of these has rank, Q choose I. There are Q choose I faces for a simplex. It gives us a resolution which is of the form.
Sorry.
Yeah.
What is the LCM of M1?
It's the least common multiple of two monomials.
M1?
Oh, LCM of M1 is just M1.
Oh,
I
okay.
should have, because I did from 2 to 1,
I see,
so
that's good.
it should really be LCM of M1, M2 to Mi, and then one by one you delete.
And should there be a sum there in the second term?
I'm sure there should, I missed it.
And,
Yes, I missed it, thank you. Yeah, please speak up, I'm prone to many typos. There's no eraser here, is there? Oh, there it is. So here's what the Taylor resolution for any monomial ideal will look like. So any monomial ideal with Q generators, you can take it square free, it doesn't matter. So it's going to look like R to the Q choose 0. I'm writing the total Betty number right now. I'm not bothering with breaking it up. Then R to the Q choose 1, R to the Q choose 2, and the very last one, what is the biggest space? There's only one of them, and it's just R. And then we're done. Okay? So this is Q choose Q, which is 1. And this is also 1. And here I'm taking the resolution really of R mod J. Okay? So the point here is that this is a resolution, and it's numerically easy to compute. Every Betty number has a binomial bound. And the most important thing of it is that it's realized. So that means that there exists monomial ideal J such that beta I of R mod J is less than or equal to Q, is actually equal to Q choose I with Q generators. That will follow. Okay? Any questions so far? So the Taylor resolution is realized, but once you take a monomial ideal and you take it square, the Taylor resolution will never be realized for a square. And the reason for that is, so I will show you in a minute, but basically what makes the resolution minimal is that every entry in the matrix that you write is not a scalar. It's equivalent to that the image has to be inside the maximal ideal. So when you do the square of an ideal, you find situations where the LCM of the face and the LCM of the subface will always match. Okay? So for that one, it's the multigraded that is going to determine that. So observe. I'm going to switch to square free right now. Actually, this is true even for non-square free, but okay, so observe J squared never has a Taylor resolution. It has a Taylor resolution, a Taylor minimal resolution.
So Sara, I'm kind of confused. What does it mean this resolution is actually realized?
It means that there exists an ideal J whose, okay, so this is a bit of a total Betty number is actually Q choose I, but What it actually means is that there exists an ideal, okay, this is what it means, I'm gonna write it in.
Are you just saying that it's minimal? You're just saying it's minimal resolution?
Yes, yeah, we're always talking about minimum. So Taylor resolution is usually big. Every ideal has a Taylor resolution.
Right, that's why I was confused.
So it's actually realized as a minimal free resolution of some J. So when I say it's realized, it means is it realized as a minimal free resolution.
You started with a J. This is a
I
different J.
started with, if I start with any J, so for example, let's do an example here. If I start with J equal to X, Y, Y, Z, Z, W, right? Then what I notice is that if I do the Taylor resolution, so let me just label these. Three generators is a triangle, so X, Y, Y, Z, Z, W. Okay? And here, the middle is going to have the LCM of all three, so it's X, Y, Z, W. And this edge is also going to have X, Y, Z, W. There is a reason for this, and the reason is really this is a topological cone. It gives you a topological cone. So what happens is, in the matrix of the differential map, this edge, which is the boundary, one of the boundaries of this triangle, the homogenized version, these two cancel out. So when you go from R3, the third part is R of the triangle. So this is the Taylor resolution. So let me just write it out. Taylor of J. It's not minimal, which I will show. It has one triangle, three edges, and then three vertices, and one empty face. So it's going to look like this. And then when you go from the triangle down to the edges, there are three boundary maps you take. This thing, it's rank 1, goes to three edges. And the entries of the matrix are going to be the quotients. So X, Y, Z, W, but this one gives you a 1. And this one is X, Y, Z. So that will give you an W. And this one is Y, Z, W. So that's going to give you a, someone told me I should put X. No, X, yes. So what's happening is that there is this extra copy that you should pull out. So this and that should actually go away. So there is what we call a trivial sequence. This exact sequence is the sum of the one with 2 and 0 here with this trivial exact sequence. So the minimal resolution is going to be only those two. So the Taylor resolution always works. It's a beautiful combinatorial way, a topological way to make a resolution because you know your differential. You do it for any simplicial complex, then there are criteria of whether it works or not. But the Taylor one always works. That's the theorem of Taylor's thesis. And it's almost never minimal. But but there are always ideals. So any simplex does support the minimal free resolution of some of them. This is also.
So that's a different J, okay, I guess.
Now I'm looking at any J. Most of my talk is about any J, any ideal. So I'm saying, so this resolution is actually realized, yeah, so in this case, you can just take three variables. Actually, yes, you can take three variables. X, Y, and Z would have given you X, Y, Y, Z, X, Z, and then X, Y, Z in the center. That would be a scarf ideal. And this is basically a result of Peva and one of her students, that any acyclic simplicial complex is going to appear or support the minimal free resolution of some monomial ideal. That it's scarf ideal. That's what it's called. Okay. So there always exists one for which the simplex is minimal, any acyclic complex is minimal. But what I'm saying is, if you take any monomial ideal and square it, then the simplex is never minimal. This is what I'm saying. That means the simplex, when you label it with the generators of this square, you are always going to have repeated labels for a face and a subface. So this is what I'm saying. I'm saying, observe that LCM, so J squared is going to be, if J is generated by M1 to MQ, then J squared is generated by, in the best case scenario, all Mi and J's and all Mi squared, or I, J, actually, I can even write less than 1. And so the best case scenario for the sim, because you usually want to do a resolution that is small as possible because you're actually interested in a minimal free resolution. So your best case scenario is where you have a minimal generating set. So you can take the smallest number of vertices and make the smallest topological object. The dimension of the object is a bound on your projective dimension. And so if you square, you might get all of these generators, or you maybe won't get all of them. But again, think generic, think every possibility. That's the biggest number of minimal generators you have. But then you have that M1 times M2 always divides the LCM of M1 squared and M2 squared. This always happens. Which means no matter what your simplicial complex is, that it will have, if it's a simplex, this is going to be contained in the Taylor complex. This is the face of the Taylor complex, which is M1, M2, M1 squared, M2 squared. And this triangle and this edge are going to have the same label. So O is equal to X, and so this resolution cannot be minimal. Because every time you write a topological resolution, it could be a cell complex, a CW complex, it's always boundary maps. And inside those boundary maps, if you have a triangle, you have to always write it as a sum of edges. Then you homogenize, and every time the triangle and the edge have a matching label, you are going to get a 1, a scalar. So the resolution will be minimal. Okay, so what to do? So the idea is that what do you replace a simplex with, or what is the power of a simplex, so that it satisfies this. What is the counterpart of the Taylor resolution for the second power and for the third power? So the question is there a simplicial complex I'll just call it delta R, that satisfies, let's call it delta RQ, I'm just making this up, that supports a free resolution of I to the R for every I generated by Q square-free monomials. So obviously the Taylor complex can do that for every R, and is minimal for I to the R for some. So it's actually a minimal free resolution of something. So this was the quest. And we actually, well, we managed to find an answer, which was almost good. So for if you let R equal to 2, so let me go back here. So
Sarah, the last statement, is this after the and symbol, is this equivalent to there exists square free monomial ideal J for which this resolution is minimal for J to the R?
yes, so for every I, it's a free resolution, and for some I, it's a minimal. So,
And this is a question of the embedding numbers.
it's about the whole resolution,
Or you
because
also
in
want
the
the
end, it's a, sorry?
Or do you also want the differentials?
The differentials, yes, but it will follow. What we prove is actually for the differentials, but and a lot of people don't care about the differentials. But basically, the idea is it's always a simplicial resolution. So the way you do it is you actually construct the chain maps, you homogenize them. That's the proof. Yeah, so you get a whole resolution. Okay, so any other questions? Now I'm afraid to look at the watch because this was supposed to be 10 minutes. But anyway, I'm going to tell you right now. The answer is we could do this for R equal to 2, any Q, we found something that is actually realized. So answer, that question is R equal to 2. Yes, this went into the proceedings volume of the WIPA meeting, so this was quick. We managed to do this one. So for example, if Q is equal to 3, so that means if I have I is equal to M1, M2, and 3, so if I square this, I'm going to get 6 generators, so it will be a 6 simplex that is going to be 5-dimensional. Which gives you a projective dimension bound of 5, but we managed to show that I squared always has a free resolution supported on this picture. And I will label it, so this is M1 squared, M2 squared. Because this is a prototype that is supposed to work for all monomial ideals, not all monomial ideals may have all of these as minimal generators, but some of them do. So see here, I've taken care of the unpleasantness of M1 squared, M2 squared having the same LCM as the triangle with also 3 of these vertices. So we managed to prove via various methods that this always works. And actually this is called L2Q. And the L is in honor of Gennady Lubeznik because this is it's a generic version of the Lubeznik resolution. And a Lubeznik resolution will not do it for you. But if you do several Lubeznik resolutions, imagining changings of M1, M2, M3, and you keep in mind that a minimal free resolution is always unique. So once you manage to get rid of some face or some degree in some resolution you find, that degree is not necessary for a minimal free resolution, because then if you have some resolution that doesn't include it, then the minimal free resolution is included. So that's basically the idea of this. So this is for, this is a Lebesgue resolution in spheres. So this was quick, and then we did L3. Oh, actually, no, we did LRQ. So LRQ, that means any R, any Q, but almost never minimum. So basically, these are too big. Nice, but too big.
Too big means that they're
Never minimum.
never normal.
So there is no I for which I to the R has a minimal free resolution supported on this LRQ. No I with Q generators. So what is the power, the Rth power of a simplex? And actually, this is no longer this is the name of our project, but it's no longer the correct title because the counterexamples here show this the Taylor resolution, which is a simplex, works for any monomial ideal, not just square free ones. And we need more faces for general monomial ideals. So I shouldn't say power of a simplex, but square free power of a simplex. So the question of realized or not realized is what brought extremal ideals about. So like I said, we have an LRQ, it's too big. We have an L2Q, it's right on. So who realizes the minimal free resolution? So extremal ideals do. So Q extremal ideal Q has Q square free generators and here's the theorem of the Wycliffe group. For every I square free with Q generators, beta I j of I to the R is less than or equal to beta I j of EQR for every power. So that means the Taylor simplex. So L1 is the Taylor simplex, by the way, as you can imagine. I'm going to make a note here. Or you can say it's a simplex. So this is even better than that. It's like even the I can replace this with M's, multiplicative M's. Okay. So this is how the extremal ideals came to be. And as a result, the power of a simplex, although that's the wrong title, is whoever supports a minimal free resolution of this. Okay? So one goal here would be the best power, call it an idea. Best power or best Taylor to the R would be a complex supporting a minimal free resolution EQ.
Can I ask you a question?
Yes.
Are you in a fixed number of variables?
Yeah, so you can let Q and R move, but every time you fix a Q, you find EQ, and that EQ is going to dominate all square free monomials with Q generators.
But
And then you take the powers.
but the polynomial ring is a fixed polynomial ring, right?
Yeah.
You're not, okay.
I mean, okay, so this EQ lives in another polynomial ring. We have a ring map that's the point.
Oh, that's what I'm asking.
Yeah.
So it's in more variables.
Oh, yeah.
Yeah, because that's what I was
It has
thinking, you
two to
could
the, it
factor
has
them up.
two to the Q variables.
Yeah, okay, that's how.
Yeah.
Okay, I was
It
just
has
guessing.
all
you could
possible,
do
it
that,
has all
because
possible.
you want to have.
Okay, so here I'm gonna just say one thing is that not every monomial ideal has a resolution supported on a topological object. This was a really nice paper of Maurizio Velasco, like about 15, 20 years ago. We found these big classes with 23 generators. You can't even find a CW complex. You can't find anything that supports their minimal free resolution. So, I mean, this might be a task that you can't do, because now I'm not saying even any topological object, I wanted to be simplicial. But the thing is that we actually believe that these are scarf ideals, which means they're LCM, which means that basically in the multigraded resolution, every monomial, every LCM appears exactly once. I'm not going to define scarf ideals, but that's the base. The scarf multi-degrees, which are LCMs that only appear once, live inside every resolution. So that's what you build your resolution on, and we believe these are scarf. So we have a polyhedral definition of these with some 4 of us who went to MFO and just did that in terms of half spaces. And then we spent a year and a half, like 30 something plus pages, to just do the case R equal to 3 to prove that these are scarf and actually find the resolution that is realized. So it's really, really hard in terms of combinatorics. And that's kind of the point of this talk, because we didn't know why it was so hard, and I still haven't defined extremal ideals, but the point is that then we discovered that things like integral closure, symbolic powers, things that people work a lot to find little things, symbolic defect, and so on, all of them are dominated by these DQs, and these people don't know. So that's why it's hard. So let me define extremal ideals. How much time do I have? 15? Oh, wow. Okay. So EQ is generated. The Q extremal ideal is generated by epsilon 1 to epsilon Q. So it has Q generators, which are square free monomial ideals in this polynomial ring, which I call SQ. So this bracket Q means the set of numbers from 1 to Q. And this is the polynomial ring over the same field, whose variables are YA. They're indexed by subsets of Q, where A, I'll do better, I'm gonna do it, right big. The subset of SQ, which is K of Y sub A, where A is a subset of Q. Okay? And each epsilon I, the little epsilon I, is defined as the product of Y sub A, where I is an A. Okay? So E3, I'll do E3 somewhere, I'll do E3. And E3 is the one that is your prototype, has E3 squared, has minimal free resolution supported on this. So when Q is equal to 3, epsilon 1, so epsilon 3 is generated by little epsilon 1, little epsilon 2, little epsilon 3, and in the polynomial ring K of x1, oh, sorry, y1, y2, y3, y1, 2, these are sets, y1, 3, y2, 3, and y1, 2, 3. Okay, so it's a big, big polynomial. And epsilon 1 is y1, y12, y13, y123. Epsilon 2 is y2, y12, y23, y123. Epsilon is y3, y13, y23, y123. You can see why I don't want to do a bigger. And it's very computationally expensive. So yeah, I'll probably forget to interested in computations. These are really challenging to run because they are expensive to run, but for extremal, for every Q and every R, a lot of the property P, the idea is to run them once, don't ever run them again, keep it in the database. And then there is the ring map that is going to refer to that database to determine property P for any other given idea. So that's how the computation should run in my point of view. Okay, any questions? Yeah.
I don't see how epsilon q I. Like, if you want to.
I'll do that now. So that's the next thing. So take does epsilon q relate to I equal to m1 mq. So these are square free. Okay, so that's the question. And the answer is it's by I. And actually this talk is really about the map CI. Because that's the one that changes with the ideal I. Extremal ideals are just there. They don't change. So the answer is that there exists a ring map CI going from your SQ to your ring R. Okay? So how does this CI work? Okay, so that's also answer. So that's a little bit it's not very hard, but it's a bit technical. So basically, what you do is that you list your monomials. Okay, so build subsets A1 to AN of Q. Okay. And remember, each one of your monomials, each mi, is the product of some x's, right? So xi1 to xit. Okay. So let aj be the set of all the indices I and q where xj divides. Okay, so these A's are keeping track of which generators contain which monomials. And then CI, what it does, it takes every variable y sub A to, so Ci of y sub A, when A is a subset of Q, is equal to the product of the x, careful, I, where I is in A, and A is equal to A u for some u, So that's. So that's if A is equal to AU for some U in Q. So basically, when you build these A's are gonna take you to your monomial generators M1 to MQ, and every other subset is just gonna go to 1. I'm 42% sure I messed up some indices, but it's beside the point. There's no way you're gonna remember them from here. So, there was a question already. Okay, so, so theorem. And I'm pretty sure I have less than 10 minutes, right? 7, okay. So theorem. Let I be any square free monomial ideal of R. We have x1 to xn. Generated by Q monomials. Then, so 1, Ci going from R, no, sorry, from SQ to R is a ring homomorphism. 2, Ci, so suppose this I is generated by M1 to MQ. Q monomials M1 to MQ. So Ci of each Mi of epsilon I is Mi for every I in Q. So that means the Q extremal ideal is going to go to map onto I. Maybe I'll go backwards so I don't have to, well, I don't actually know. Let me erase this. Three Ci of EQ, it follows from 2 is I. But actually, more is true, it also works on all the powers. So, right? 4 is that Ci preserves LCM lattices. This is the LCM lattice of EQR. This set of all possible LCMs of the generators of the ideal EQR is equal to the LCM lattice of I to the R. And this allows you to do topology, simplicial homology. 5, what I wrote over there, beta I M of E of I to the R is less than or equal to beta I, so let me be careful, Cm beta I M of EQR, where you take M in the LCM lattice. So these are just the refinement of the Betti numbers. Basically, all Betti numbers are bounded, and the bound is sharp because it's realized by some square free monomial ideal, which is EQ itself. LCM of EQR. So again, R greater than or equal to 1.
Before you erase that, I have a question. I couldn't understand that. I wanted to ask a question about it.
Okay, I was gonna write what I mean. I'm replacing it with something more specific.
Okay, yeah, because to me, it didn't make sense. So there's one EQ that works for all i's generated by Q elements. So
Yeah,
didn't see how
so
they
it
could.
works via CI. So, so it's the CI that matters. Like I said, you do everything for EQ once, EQR once, and you're done with it. So 6 CI preserves intersections. And K ideals of SQ. I'm going to cut through the chase. CI preserves associated primes. So you should take this with a grain of salt, because some of these primes collapse onto one another. But basically, questions about persistence of associated primes, the bounds on persistence, and all of them can come by studying this one. So it's going to be S of L to the R. So I'm going to put a quote here because it's not one-to-one, some of them go together. 8. What else is that? Primary decomposition. CI. Yeah, we'll write it colloquially. Primary decomposition of PQR is going to give you the primary decomposition of I to the R. I lost track of my numbers. What is the 9? Okay. 9 CI EQR bar. This is integral closure. Is I R bar. So for example, a corollary is that I think all square free, if okay, Q less than or equal to 3, then I is normal. All of its powers are generally closed. This comes because you can compute the analytic spread with Q equal to 3 easily, and there is a bound for computing. There is a bound for how many powers do you need to go to calculate the integral closure before you can determine that the ideal is normal altogether. The bound is given by the analytic spread, and in this case, for monomial ideals, it's a combinatorial formula, and in this case, you only have to compute EQ and EQ squared, and so for Q equal to 3. So it ends up, and then all you can do is run Macaulay 2 for E3 and E3 squared, or you can use the symbolic polyhedron, or you can, the Newton polyhedron, etc., etc.
So, Sarah, the E that you're writing down depends on the generators
Q, yeah.
of I.
Yeah.
As well.
So I has always Q generators, and then we can let
Well,
R.
not just the number, but the actual generators.
No, the CI is not the actual generators. Q is the number of generators.
So
The CI determines where you're taking this EQ.
So the extremal ideals are
Fixed.
fixed, defined independently of the generators of
Only the
I,
number of them,
but
right?
that's only the number. But then the map CI
Yes.
depends on I itself. Okay, got it. Now,
So CI, I'm sure I'm forgetting stuff, but there's lots of things like that. The symbolic power is the symbolic power. So A stack, things like that, all of them come out of this.
Is EQ R not integral closed?
EQR is not integrally,
I'm asking,
So,
it
in
feels like it
general-
might always be.
no,
but
because
it's
then,
not.
no. No, it shouldn't, because not everything else. EQR is pretty badly behaved. It's not a mix, it's easy to define, but. Yeah, but for example, things like persistence come from here. Like there is the counterexample to persistence problem associated primes for square free monomial powers of square free monomial ideals. Some computer scientists found it, and it was 16 generators. But you know, if you run EQ enough, you can find counterexamples because EQR must not satisfy persistence because of this method, because the associated primes come from here and the primary decomposition comes up there. So you can run an example and maybe find one with 5 generators, but it's expensive to run. This is the thing, someone has to just run this example. So our younger people are doing it and making a database. What else? Yeah, I think I'll stop here. I think this is enough. Pretty much, CI is magical. There are lots of things you can do for standardizing theory. A lot of it is work in progress. There are many, many questions that can be answered in this way. I wanted to just tell you one last thing about D-extremal ideals, which have been working on again with the Wicca group for the past year or so, and it's transformed into a much bigger project than we intended it to. But basically, you can mimic all of this, but take a monomial ideal where you know that M1 divides the LCM of M2 and M3. Like there is a divisibility. You can model that divisibility and make a refined extremal ideal for that divisibility. And again, do the whole thing. I don't know how much of it will go through, but the map is the same, so it all should go through. For ideals that satisfy certain fixed divisibilities. So for all square free monomial ideals for which M1 divides LCM of M2, M3, for example, or more. Maybe I should stop here.
Are there further questions?
I want to see an example that's not nearly close of an EQ.
My advisor was very strict.
Just want to, I hope I understand it.
Yeah,
There's
there's
an
I could
SQ
be wrong.
there's
because
an
lots of
SQ
things I say are
action.
usually wrong, so you should take them all with a grain of salt.
There's an SQ action on that thing, and there'll be an SQ action on the end closure of it.
Yes.
And I feel like since every, that it's somehow, I don't know, I have to.
So there is
I want
an
to see your
SQ
example.
There is an SQ action. And yeah, I will
I want to see it.
Okay,
Just
we'll
the
talk.
example, that'll help me
Yeah.
understand.
yeah.
There are further questions? Okay, if not, let's thank Sarah again.